Understood about how hypothesis testing works, one of the big things that I left out in the previous video was how to compute p-value, right? Because this is the most important step, because we decide to either accept the hypothesis, accept the null hypothesis, or reject it based on the p-value, right? We will see a very, very interesting technique of computing p-value called permutation testing. Okay, it's called it's a very, very interesting idea. Let's see how it works. Okay, so let's assume I have a class. I have my class 1. Let's assume these are all my observations from class 1 of heights, 50 heights here, and these are my class 2 observations, right? Student heights from class 2. Let's assume I have 50 observations here and also 50 observations here. Permutation testing works as follows. So I have 100 heights here. Literally, I have 100 heights between these two, right? I have 50 heights here and 50 heights here. The first thing I do is I take these 50 numbers and 50 numbers and put it into one big set. Okay, and then I jumble this set. Okay, I completely jumble this set, right? When I jumble this set, as soon as I jumble this set, I do one thing. I do the simple operation. What I do here, okay, before we go there, before we do see what we do after we jumble, let's assume the mean height here is mu1. Let's assume the mean height here is mu2, and let's assume the difference in these heights is delta, capital delta. Okay, now after I jumble, what I do is, okay, so let's just keep this. So I jumble, and after I jumble, what I do is I randomly sample 50 points. I randomly sample. This is important. It's important to randomly sample 50 points and put it in a vector called x. Of course, when I have randomly sampled 50 points, the rest of the points can go into the other vector, right? For these two vectors, now I compute the means. Let's call them mu1 and mu2. So this is my first time I'm randomizing it, right? So what I've done here is I've just combined these 100 observations into one big set, right? I've jumbled this set and I've randomly picked 50 examples into a vector x, which means the rest of the 50 examples go into a vector y. Now, if you take the difference of this mu1 and mu2, let's assume I'll write it as small delta 1, because it's the first sampling that we did. Now imagine from the same set again, I resample, right? Again, now I get my x and my y. Again, when I sample 50 points into my x randomly again. Randomly is important here. It's extremely important, right? Now again, I get my mu1 and mu2. I subtract these two, and let's assume I get a value of delta 2. Suppose I repeat the same process where I randomly pick 50 points into a vector x and keep the rest of the 50 points in a vector y, and I take the means of these two vectors and subtract them to get deltas, right? If I do this, let's say 10,000 times, right? I get my delta 10k. These deltas are important. So what I've done is, let's quickly recap that. That's important, right? So I have 50 points in my class 1 and 50 points in my class 2, and the difference of means is capital delta. Okay, the difference in means is capital delta. I put all of these 100 observations and jumbled them up and kept randomly sampling 50-50, and I've sampled it 10k times. For each time I sampled 50 points, I took the difference in means of the first sample, the first 50 and the second 50, and I got these values as delta i's. Now, as soon as I get my delta i's, what I would do is I would sort my deltas, my small deltas. Let's assume I sort them and I get delta 1, delta 2, let's say delta 10k. I'll just put a dash here because I've sorted them, right? These are all unsorted. Suppose if I sort them, let's assume I get my deltas like this. Let's assume amongst this, so I also have my capital delta, right? Which was actually the difference between class 1 mu and class 2 mu, right? The original one. So this original one. Now I'll say, where does my delta fit in here? This is my sorted order. Let's not forget that. This is your sorted in increasing order, let's say. Okay. This is sorted in increasing order. So if my delta is here, and let's assume there are let's assume 5% of points which are greater than delta. Okay, then I would say that my p-value is 5% or my p-value is 0.05. If let's assume there are 20% of points here, or if there are x% of points here, then my p-value basically becomes x, right? Or instead of writing x as a if this is 20%, we could write it as 0.2. This is how we compute p-value. Now you might ask, okay, you come up with a method of computing p-value, but why is this intuitively the right way of computing it? Let's take a step back and understand what we just did. What we just did was, by combining these 2 points into one big set of 100 points. So this set actually has 100 points, right? We said that let's assume that there is actually no difference between these 2 points. These two classes of students, these two sets of students, right? I put in a big jumble. Let's assume. So by jumbling, what I'm assuming here, I am assuming that there is no difference. I'm assuming my null hypothesis. I mix both of them, and now I say that let's sample them. If there was no difference, if I randomly sampled 50 points, of course, when I randomly sample, I could get some points from class 1 and some points from class 2. So if there is actually no difference between heights of students in class 1 and class 2, my x and y, right? My x and y would have my mu1, mu2 values very similar, right? Now, imagine if there was actually no difference between heights of students of class 1 and class 2. Then this value, let's assume, is 10 centimeters. Just let's understand that. My deltas can vary, right? My deltas could be 0 in some cases, but because I've only sampled 50 points and not 5 million points or 500 million points, then you'll get some values which are 10, some values which are 5, some values which are 2, etc., etc., etc. Now we are saying that if there was no difference, by actually combining these two into one set, we are saying that imagine that there is no difference, which means we're assuming our H0. Now, if I randomly break this 100 students into class 1 and class 2, what differences would I get? Right? Now, if the actual difference that I got, that I observed in my sampling, the actual difference that I observed in my sampling, if it is if it is greater than 95% of my points, right, which means it's not actually random, right? The probability of this happening, the probability of my delta happening. So what we're measuring here is what is the probability that you'll observe a value of delta, assuming that there is actually no difference, because each of these sets assume, because I've randomly sampled them into class 1 and class 2 here, or x and y, I'm assuming that there is no difference. So by assuming H0, what is the probability that I'll observe values which are greater than equal to my delta? If that probability is very, very small, right, then I should reject my H0, right? That's why when we get a small p-value, we end up rejecting our H0. When we get a large p-value, we say, oh, this is highly likely. So let's assume my p-value is 20%, right? What it means is there are 20% of my deltas which are greater than my small deltas. There are 20% of my small deltas that are greater than or equal to my capital delta, which means if I make an assumption that if I assume H0, which means there is no difference, and I'm simulating that there is no difference by actually combining all these points and sampling them, right? So when my value is 0.2, it's like, okay, there is a 20% chance if things were fully random, there is a 20, because I have only 50 samples, there is a 20% chance that I can observe a value which is as high as delta. So I'll say, okay, since I'm not very confident, it's only 20%, right? It's not like 1%. It's actually 20%. And hence I'll say, I will accept my hypothesis 0, which is the fact that then my hypothesis becomes a fact because I've accepted my null hypothesis H0, right? So you might ask, what is the typical p-value that people typically use? In most of scientific computing, people typically use a p-value of 0.05 or 5%. This is called 5% significance level. But what is the right answer? There is actually no right answer. It depends on how sure you want to be. Because in some experiments, people actually take a p-value of 0.01, especially if you're in areas like medicine, right, where you want to be really really sure whether your test is working or not. You will use a p-value which you want to ensure that your test is not random. It has to be as far away from random as possible, right? In such cases, you would say you would use a p-value which is very small. Typically, people do not accept null hypothesis. People do not accept alternative hypothesis if p-value is greater than 10%. So the right p-value, oftentimes you'll see in a lot of literature and articles that they use a p-value of, not 0.05 or 5% significance, right? But there is no right answer on whether 0.05 is right or 0.01 is right. It's very, very application dependent. Now you might ask, okay, all this concept is brilliant, but this whole hypothesis testing is very old. Our computer science, because here what we have to do here is we have to do all this simulation, right, computationally. All this sampling, everything has to be done, and we have to do it 10,000 times, right? All of this is possible today very easily using modern computer science, because I can write a simple computer program to do 10,000 samplings, right? It's very, very straightforward. What did people do in the olden days when they couldn't manually do random sampling, right? They couldn't say, okay, let me toss a coin these many times and I'll repeat this experiment. So in those days, what people did was very interesting. People said that given my deltas, mathematicians discovered that your deltas come from a distribution. For example, let's assume your delta came from N01, which is normal Gaussian distribution with 0 mean and 1 standard deviation, right? Let's assume if we know that in this problem your deltas came from a normal distribution, right? Then you know that N01 has its mean at 0, right? And let's assume I observed my capital delta to be 2. Let's just say, right? This is my 1 and this is my -1 and -2. Let's assume my capital delta was 2. Now my question here is, since my capital delta is 2, what is the probability? And I also know that my small deltas come from a normal 0-1 distribution. So in the olden days, in the pre-computing days, and again, computer science is modern computer science, and availability of programming is only 50, 60 years old, right? Prior to Second World War, people actually tried to understand what is the distribution of your deltas. If your deltas come roughly from an N01 distribution and you observed a capital delta of 2, then you would say, oh, that the chance of observing a value this high or a value higher than this is only 2.5%, right? Because in a normal distribution, you know that there is only 2.5% of points here, right? And there are 2.5% of points here, right? So you would say, I got a delta value which is very high, and the probability of getting a value of getting a value this high or something higher than this, right, is only, so what is the probability that your delta is greater than 2, right? It's only 0.25, sorry, 0.025, 2.5%, right? So then you would say that my p-value is 0.025. So a lot of pre-computer science or pre-simulation or pre-computing hypothesis testing had to come up with a distribution to fit your deltas or to fit your simulation results. Because this is a simulation, right? Because I'm doing random sampling of 50-50 points and I'm doing 10,000 sampling. This cannot be done by a human being. 10,000 samplings will kill you, right? So in those days, what people did was they tried to fit distributions. Again, this is one very nice application of distributions to real world problem solving.